When we first open a book on general relativity, a single thought always hits us. Why does this feel so difficult? The answer is deeper than mathematics. Now, general relativity has got a common notion that the subject itself is difficult and complicated. The first idea for this is that the usual notion of force, which we learn in Newtonian gravity from F equals to ma, changes to something which is called a space-time curvature. So it is no more a force but something abstract which is called a space-time curvature. The concept of straight lines or the Euclidean metric now changes to what is called a geodesic notion, which looks a little bit complicated, but if you learn it will be fairly easy. The Einstein field equations comprises of lot of tensors and other notations, and the Riemann curvature tensors looks like a monster right in front of you. So overall we can say that this is a theory which is packed with lot of exotic and complicated mathematical notation and ideas that are seemingly hard to grasp, ideas which are abstract. Now, general relativity itself requires an intuition and a different kind of an approach. First is that, as you have already seen, the heavy mathematics makes the student or you will fear that whether I will be able to learn general relativity or not, because it is fully loaded with heavy mathematics and lot of complicated notations. Second thing is that general relativity requires a balance of both physics and geometry. So if you're selecting a book, that book needs to balance with something which is called a perfect balance between physics and geometry. Third thing which is also important is that general relativity requires building intuition about curvature, geodesics and space-time. So remember that if you're selecting a book, that book should have a lot of diagrams, visual explanations and analogies. Not every book or every textbook does this so well. Not all books of general relativity is also not, which is something following what we call a learner-friendly sequence. That means some books start with full of tensor notations before explaining why it is needed. So you need to get a book which actually respects and tells you the historical and conceptual flow of how general relativity was developed, equivalence principles, and so on. Everybody, every single person, you will see they struggle with which are called tensors and Christoffel symbols. So the right book will introduce these ideas slowly and clearly instead of assuming that you already know them. And your understanding of general relativity depends on how clearly it is explained. So as you know that even the toughest ideas becomes accessible if it is rightly explained. So that is why selecting the right book is not optional. I would say it becomes whether general relativity becomes enjoyable or frustrating depends upon which book you select. So from here we move to the next part of our video where I would like to explain you some of the very important critical success factors or factors you should consider before selecting a book. Those who are old subscribers and those who know me and those who are watching for the first time, you must have noticed that in this channel I've made lot of reviews about different books of general relativity, from Leonard Susskind to Carlo Rovello, Robert M. Wald and the very classic Bernard Schutz. Now all these books are great, but you should remember that every choice actually opens up a door but also countless other actually closes. So that means with each decision comes the responsibility of knowing what you leave behind. Now, if you have watched the famous film which is called Matrix, where Neo and Morpheus has been talking to each other, there is a quotation which tells, you take the blue pill, the story ends. You wake up in your bed and believe whatever you want to believe. You take the red pill, you stay in Wonderland. And I show you how deep the rabbit hole goes. Now, this is a very famous and a favorite quotation of mine where Neo and Morpheus has been telling. So the ultimate bottom line is the choice. What is the choice that you're making? That means which book you're selecting. A very good book will make the subject very interesting for you, and a bad selection will ruin the subject, and you will forever think that general relativity is a difficult subject and it is not meant for you. So decide whether you're going to take a blue pill or the red pill. However, There are certain important factors which I will like to point, and I hope that you will keep it in your mind for selecting not only a book on general relativity but any kind of a book. The first thing that I would like to tell you is that you need to start with what you are comfortable. So you should not select a book because it is the bestseller or it is a New York bestseller or your friends have told. Just understand that what you are comfortable with, it is intuition, heavy mathematics, depending on that you need to select the book. Second is that, as I was telling, whatever you select, what you're comfortable. If you prefer intuition, fine, go ahead. There are many books on that. If you prefer heavy formalism or mathematical rigor, you can go ahead with that. And do not select or choose a book that just appear because it is popular. So you just select a book because it is New York bestseller or it has been told that it is one of the best book, but it might not suit with you because your comfort zone is something different. Also check in whether the book that you're selecting is building the concept step by step, because general relativity itself is heavy in mathematics, heavy in terms of physics. So you should look forward for a book that builds on concepts step by step. Also, as I just explained that it connects mathematics with physics, so select a book that connects with the mathematics and the physics part. If you are a pure beginner, if you are starting to learn general relativity right from today, you should avoid books that are very much technical and that which starts with too much of mathematical formalism. General relativity itself is abstract. So what you need to know is that in order to visualize those abstract concepts, select books which contains lot of diagrams, lot of visual intuition. And I will show you about that what I am talking in today's video. Also prefer authors who explain why, not just how. That is also very important. And make sure that there is a kind of a logical development of historical facts which will make the understanding much better. So remember this, that a wrong textbook can hold you back, leading to a lot of misconceptions and also frustrations, and turn general relativity into a far more difficult subject which actually it is not. So please check out the following points: that what is the level of rigor that you want a step-by-step approach, a mathematical formalism or an intuition. There should be a balance between concepts and computation. That means whatever the concepts have been told, whether they are matching with that. The mathematical prerequisites, if you're going in tensor analysis or differential geometry, do that book or does that book contain the level of mathematics that you are targeting to? If not, does this book give you a kind of a refresher or kind of a quick understanding of the basic mathematics? And finally, I would say the level of abstraction. This is very important. Prefer something which is example based, which is low in terms of abstraction, and advanced learners go for abstract treatments. So when we talk about those key factors for selecting the book, what are the things that you should keep in mind? I would now come to the central part of the book which I would be talking about, and I will be also explaining why this book is great. This is called General Relativity for the Gifted Amateur, and it is written by Lancaster and Blundell. Now this is the cover of the book which is available in Amazon, and here you can see the customer reviews. 88% are making it 5-star, and these are some of the snapshots which I have taken from Amazon. Some of them are from German, some of them from Spain, so I have translated in English. So more or less it tells that it is a wonderful book, great book, an absolute a masterpiece. It is an absolute masterpiece. All those things actually proves that this is really a great book to go about. Now, one thing which kept me busy about this book is that why it is called for the gifted amateur. So when I did a little bit of research, what I found is that the phrase gifted amateur is selected for the following reason. Number one, that means it is not meant for casual amateur. That means it's not a book which you will just, sit on your sofa, enjoying with a cup of coffee and cookies. It is not meant for that. It is meant for motivated one. So that means it bridges the gap between popular science and what are called graduate textbooks. Also, it encourages a lot of independent exploration, and it honors the tradition of great thinkers who were gifted amateurs. That means that book contains a lot of mathematics, lot of mathematical rigor, but it is a kind of an amateur, but for the gifted amateur. That means you should be serious in studying that, intellectually capable and highly curious readers who are not professional physicists, but they have got a kind of a mathematical maturity, and you're really sitting down with this book with your pen and paper and doing the necessary calculation to understand general relativity. So that is why it is called a gifted amateur. It is not a pure amateur book that you can just sit around and enjoy. So you have to be serious while reading this book. Now, quick review about the authors of this book. Professor Tom Lancaster. He is a professor of physics at Durham University, a very favorite university from where I have made several podcasts with their scholars. Before that, he worked as a research fellow at Oxford University, and Professor Lancaster brings a real research experience plus a passion for pedagogy. Stephen L. Blundell, he is a professor of mathematics at University of Oxford and a professorial fellow at Mansfield College. He is living with his wife, who is also a professor, Professor Catherine Blundell, and in 2001, he was quoted in the magazine Science saying that ultimately your marriage is more important than your career. From here, what we move next is that how do we learn general theory of relativity, and you will be surprised to see some of the facts which I am telling right now will exactly match with the logical flow of the book that I am talking about. Now, as we always start before curvature, we will start with what is called a flat space-time. So the geometry is pretty easy. It is a first step before we go into the complicated mathematics of curvature. So because it is about curved space-time, you should start dealing with curvature, flat space-time before you go in curvature. Space-time is flat, the mathematics is easy, Minkowski space-time, and all those things you can look in my other videos which I have talked about. Step number 2, once you have mastered what is called flat space-time, you should move in what is called curved space-time. So that is why I have written only when with the flat space-time is clear, you should go in differential geometry, which includes curvature, metrics, geodesics, tensors, etc. And this will actually show you how gravity emerges as a geometry, not as a force. So the Einstein field equations and the tensor calculus, the Ricci, the Riemann curvature tensor, the manifold, etc., all will start making a meaning when you go from flat space-time to curved space-time. Now here is a quick note. Most of the students, you can jump directly in curved space-time. There is no problem on that, provided that you have got a very good understanding of flat space-time. By flat space-time, I also include special theory of relativity, which is basically made on inertial frame of reference. The third step that we go from curved space-time is what we call cosmology. So this is basically applying general relativity to the universe. So here you can see that Einstein's equations becomes a natural extension. The universe itself is the biggest solution of general theory of relativity. So but before doing that, please make sure that you understand concepts like expansion, scale factor, Friedman equations, and these are impossible if you are not learning step number 1 and 2, that is flat space-time and curved space-time. The fourth step that you should go forward is to understand what are called orbit stars and black holes. Well, these are actually what we call practical astrophysical applications of general relativity. So you understood flat space-time. then we went to curved space-time, then you understand the cosmology, applying general relativity equations to the universe, and then you start seeing that how this can be made in astrophysical applications. That means how the black hole structure is made, what is called stellar equilibrium, what are orbital motion. So these are what we call experimental checkpoints of general relativity. That means whatever the equations that we have in Einstein field equations, these are not pure equations on pen and paper, but these are actually applied in different astrophysical applications, and it is showing that yes, whatever the equations we have on our on the theory is actually matching with our observations. So that is why it has been done through experiments, and it is called experimental checkpoints. Now, the next fifth step is basically studying hard mathematics. I mean to say not hard, but the real mathematics part, that is what is called the geometry. So here you actually revisit and start learning what are called manifolds, differential geometry, advanced tensor analysis, etc. because this is the backbone of general relativity. Without going through this, it would be again very superficial. And finally, you will come to understand what is called classical and quantum fields. So this is the area where general relativity is extended, and now it is being applied to quantum gravity. So this is where Einstein field equations are modified. We get modified Einstein field equation. The classical field theory get extended to quantum field theory, and how quantum mechanics are applied on the boundary of event horizon, Hawking radiation, and all those stuff. So these are the 6 logical steps which will make you understand about general relativity. Now the surprising fact is that this book which I am talking about, General Relativity for the Gifted Amateur, actually follows this step. It starts with flat space-time, then it goes in curved space-time, it explores cosmology, then it shows you the general relativity experiments, that means the astrophysical applications, then it takes you in geometry and manifolds, the backbone of the understanding of GR, and then finally it jumps in quantum gravity. So this is the, I would say, the most natural and the highly logical and yet scientifically correct and a step-by-step approach in terms of understanding general relativity. This is the sequence which most of the professors and universities they follow, and fortunately this book also follows the same sequence. Now the next thing which I would like to talk about, which when I went through this book, what I found pretty interesting is what I would title as From Newton to Einstein. Now most of the students who directly go in general relativity really don't take a kind of a very close look at how the equations of Newton are getting slowly modified in general relativity. So the first thing which is very good, the overture part of this book, which I have taken a snapshot on the left hand side, you can see it talks about this part, that general relativity under certain weak field approximation must reduce to Newtonian gravity. And that is why it is such a beautiful and profound theory. We covered almost 110 years of Einstein's publication on 25th of November 1915. So what this book tells, and what you should also understand, that any correct theory of gravity must produce 3 things. 1, Newton's gravitational force law. Second, the gravitational field equation of gaseous form. And third, it is called the Poisson equation for gravitational potential. That means this book tells that what you are building on will reduce down to these 3 basic concepts. You will see that I will show you that Einstein built general relativity basically to reduce these equations when gravity is weak and velocities are small and life is quite easy and slow. So these are the 3 important things which this book has told, and it has told right at the beginning in the overture section. So the second point you can see here, what it tells is that first is what we have seen, that general relativity must reduce to Newtonian gravity. Now the second what it tells is that Poisson equation becomes what are called Einstein field equations. Now you see this equation, you understand what it is. The left hand side is the Laplacian, the Nabla square, and the rho is basically the mass density. That means whatever mass content is there in the universe. And what it tells is simply this: geometry equals to matter. This is the Poisson equation, the Laplacian and the mass density. Now, if I take the reduced form of Einstein's field equation, it exactly tells you the same thing. Geometry is equal to matter. The left hand side G mu nu tells it is an Einstein tensor, and the right hand side T mu nu tells it is a stress energy tensor. So from here, what we can infer is that Einstein field equations is essentially Newton's gravitational equation, which is made deeper and richer, and it is made obviously in 4 dimensions, 3 spatial and 1 temporal dimension. So once you understand the Newtonian version, the Einstein version feels like a natural next step. And most of the students I have seen, they really skip this part. So the Poisson equation, a deep understanding of Poisson equation is required, so that when you go to Einstein field equation, it becomes so natural. The third thing which this book talks about is what is called mass distributions and delta function. Now, I won't take time to explain delta function. If you want, you can put it up as a comment. I can make a separate video. But what is important is this. Now, you need to understand that all the masses that you see around the universe are spread out, not spread out smoothly. Some of them spread out just like a planet or something which is moving around, and some mass gets concentrated at a single point, which is this yellow point which I am showing you. This is something which it gets concentrated upon. Now, a point mass actually has what we call a finite mass, but it is also zero in size. It is finite, but it is zero in size. Now, in general, the normal functions, whatever in mathematics that we talk about, cannot describe this concept, because anything with zero size should have zero mass. But what we are talking about, we are talking that it has got a zero size, but it has got a finite mass. Now, it is contradicting. How can a mass, something which has got a zero size, have a finite mass? So normal functions cannot describe, because in general we know anything with zero size should have a zero mass. So that is where Dirac's delta function comes in play. Now, this Dirac delta function, you can think it is a special mathematical object that helps you to represent something which is infinitely concentrated, but with a total finite value. So what I can tell you is that this Dirac delta function is a special mathematical function that is zero everywhere except at one point, where it becomes infinitely large in such a way that its total value is exactly 1. I should say that total integral is 1. So even though general relativity uses space-time curvature that we have seen instead of forces, still it needs to know where the matter is, and general relativity uses something called stress energy tensor, and for a point particle moving through space-time, this tensor again uses a 4-dimensional delta function. So this delta function, it is zero everywhere except at a single point, and the total, what I was telling, the total integral is finite and it is equal to 1. So it tells that the entire energy mass of this particle is concentrated along this exact world line. So the question now is that why do we need it for gravity? Now the answer to this is that this m, the mass density, is written as this. Now if we have already know this using the delta function. Now if we use delta function, Newton's law, or I would say that all of the mass m is located at one point and nowhere else it is distributed. Now using delta function, Newton's law becomes this, where you can see the delta function, and Poisson equation also becomes this. This Poisson equation also becomes this. And if the mass is reduced, this is the Poisson equation. So this is the Newton's law, and the Poisson equation becomes this. And if I concentrate that if the mass is a point, say for example m, the yellow m, then it reduces to this. And immediately what we get is this. Now this one which I am showing right at the bottom, this animated one, this is actually the Newtonian gravitational potential created by a mass point which is capital M. So what this equation talking about, this one which I am showing right at the bottom right hand side, it tells you how the gravitational potential changes with distance r from a point mass. It is the standard formula which is used in Newtonian gravity, when we treat an object as a point mass. So that means we can say that the entire delta function collapses, the entire integral picks out at a value at a point. Again, let me clear it out. This particular equation tells you that the gravitational potential changes with a distance small r from a point mass, and it is the standard formula used in Newtonian gravity when we treat an object at a point mass. Now, if the mass is spread out like the inside of the earth, the potential is looking like this. So we are actually collapsing the Dirac delta function, and we are getting something which is just as equivalent as the Newtonian gravity. It is the gravitational potential which is changing with r as we are moving with the distance from a point mass. Now the question is that we understand that we need a Dirac delta function because at some point m, what we talked about, this is a point where we need to know where the matter is, because it is zero everywhere except at one point. Now that is why the question is why it is important. So as you see that in Einstein's theory, stars, planets, black holes, etc. becomes a source of curvature, and this source is actually denoted by this stress energy tensor, which is T mu nu. So all these Dirac delta function, the first one is the what we call the first 1 dimension, 2 dimension, 3 dimension, they are all helping to model point masses, charges or energy. It also helps to build exact points in general relativity. It is integrating over the curved space-time curvature, and it is simplifying field equation. So the importance, why it is important, the answer is that delta functions let us treat a point mass as perfectly concentrated source in mathematics. And without them, we cannot write gravitational equations, because for particles in the Newtonian gravity or general relativity. So we need this because it is a source, and we need to define the source. And in order to define the source, we need all those things: modeling point, building exact solution, and integrating over space-time. So this book surprisingly gives a very good idea about Dirac delta function and how it is used in general relativity. So from here, what we can summarize is that first, the book revisits Newtonian gravity. That means gravity is introduced using Newton's inverse square law, which we know as this. Second, it also tells you about the gravitational potential. That means because gravity is conservative, it can be used as a scalar potential phi, which can be written as this. Now, what is this equation? This equation tells that gravity points in the direction where the gravitational potential decreases the fastest. That is the gradient. So this equation tells that gravity points in the direction where the gravitational potential decreases the fastest. Also, for point mass, we get this kind of an equation. And third is that it also talks about the Gauss's law of gravity. Now, this Gauss's law of gravity, again, what this equation is telling? This equation says that mass makes gravity converge or pull inward. That means the law or the theorem of convergence also comes in play. So this equation is telling that mass makes gravity converge or pull inward. The more mass there is in a region, the stronger the gravitational field is pointing towards it. And this links to the gravitational field to the mass density, which is called rho. So this is the third point which we are summarizing. Fourth point is that Poisson equation. Combining this and this, we get the Gauss's law, which is very important. This is fundamental. You will also find that mass distribution and delta functions, which is important, and it has been very well explained in this book, and it allows Newtonian equations to handle point particles mathematically very well. So all in all, we can say that Newtonian gravity is described using a field and potential that obeys Poisson's equation. Gauss's law shows that how mass creates gravitational field lines which are pointing in a certain direction. Delta functions helps us to describe in a precise way mathematically point masses, and these Newtonian ideas are essential because general relativity under weak gravitation and approximation reduces to Newtonian gravity. So this is the episode from Newton to Einstein, which is pretty important. Now I will come back to what you are waiting for. What is the content and what is overall being covered in this book? So as you can see, this book starts with the geometry and mechanics in flat space-time, which is an absolute must. You can start reading in this way step by step. Then it goes to curvature and general relativity. And here you can see third part is the cosmology part. You can take a pause of this and you can understand, or you can write it down. This is a perfect way to start learning general relativity. Then we go to the orbit, stars and black holes, and here you can see the black holes are being covered, and most surprisingly Hawking radiation is covered in details, and I think that is something very beautiful. Also then the part which is the geometry part, and the entire, you can see 308 till 395, everything, differential forms, exterior and Lie derivatives, Cartan methods. So what I can say you is that these are actually nothing but differential geometry section. So if you are going back to any differential geometry book, great, you can go ahead, but this also gives an understanding, and this is purely differential geometry, nothing more than that. And then you can see that these classical and quantum fields, so this is the chapter which connects to modern physics. That means how the extra dimensions, gauge fields, quantum gravity, Big Bang, all those things, gravitational waves, etc. are described. So 49 you can see from classical to quantum gravity. It gives you a fair good understanding of quantum gravity, gauge fields, Lagrangian field theory, or Noether's theorem, perfect fluid, everything is being covered. So I will now finally give you the book review, which I find quite interesting. First of all, this book contains great diagrams. As you can see, the diagrams are crystal clear. It looks something like a kind of a sketch, which even gives a kind of a better understanding. There are a lot of exercises involved in this book. The equations are absolutely clear, and it is written with proper indices so that you can understand the short forms, etc. All the chapters of the book on the left hand side, as you can see, contains a basic table of content, or what you will be learning about this book, and there are examples, and at the end there is a lot of chapter summary. The chapter summary helps you to summarize at the end what you have learned. So if I talk about the strengths of the book, this is exceptionally in terms of the structure. It starts with flat space-time and builds you slowly and slowly until it concludes at field theory. It has got very little jargons which has been used, and both the professors explains things like curvature, geodesics wonderfully, and it bridges the gap between popular science and general relativity. So that means it is not superficial, neither it is very formal, but gives a wonderful understanding. And yes, as I told, it has got a wide coverage. That means starting from flat space-time to quantum gravity, you can understand it has got a plethora of delightful equations and understanding about general relativity. Well, if I talk of the weaknesses, not much to talk about. Yes, it is for the gifted amateur, as I have justified right at the beginning. You need to have an understanding of differential equations, linear algebra, and so I have seen that the book actually makes certain steep jumps, which sometimes might come as a difficulty for learners. So from differential forms, immediately it goes into Riemann curvature and so on. And it is not a substitute for full differential geometry course, but more or less it is good. I mean to say, it is still got a simplified introduction which will give you a kind of an understanding that why differential geometry is required and how it is connected to different concepts of general relativity. So that's all for today's video. Thank you very much for watching this. If you have liked, please do subscribe to my channel Physics for Students and click on the bell icon, and keep this bell icon ringing because Santa Claus is coming and Christmas is around. You can follow me on my social media handles and write to me at this email ID. I will try to answer all your queries at the earliest. So wishing you all the best, and I will see you soon in the next video. But till then, may the good Lord be with you.